Yes. Oh, I have to. Got it. Yeah. Yes. Let me set up mine. Thank you. You're very welcome. Oh, okay.
Yeah, so welcome to the Applied Math Seminar. Today we're going to have Stathis Charalampidis talk about computation math waves and Bose-Einstein Condensates. Stathis is a professor at Cal Poly San Luis Obispo, and he's been nice enough to come over and share with us what he's been researching regarding Bose-Einstein condensates. So,
thank you very much for having me. Thank you. Thank you. It's a great pleasure. It's a great pleasure to be here. This has been actually my first time in at UCSB, so I was very much looking forward to coming over to the campus where neighbors were next door, so we can have a half drive, which is really lovely. I will talk to you about one of my research directions over the last, I would say, 8 years on the computation of matter waves in atomic physics. Just a full disclaimer, I'm a physicist by training, quite interested in numerical methods that can be used in order to understand those really cool physical systems. So the outline of today's talk is as follows. I'm interested in wave phenomena, and in particular, one phenomenon that connects to atomic physics, the Bose-Einstein condensation. Then we're going to make a quick detour and brief one by just saying a few words about Newton's method, which is, you might know that it is one of our root-finding methods that we use when it comes to the solution of large systems of nonlinear equations, but how we can actually twist it a little bit, borrow some ideas that come from numerical analysis as well, deflation ideas that we use also for eigenvalue problems and also for systems of nonlinear equations, and how we can combine all those things with numerical continuation in order to study branches of solutions to a nonlinear problem, and that will give birth to this deflated continuation method. Then, as soon as we armor ourselves with those basic numerical techniques, we're going to go through linear and nonlinear waves, linear in the sense that we're going to go through a little bit through quantum mechanics, Schrödinger's equation, quantum harmonic oscillator, and then we're going to depart from that single case, getting towards the nonlinear regime where we have interacting particles at ultra cold temperatures, giving birth to a nonlinear PD called the nonlinear Schrödinger equation. Then with that equation at hand, we're going to do a mathematical analysis of those structures using the NLS equation or the Gross-Vitesky equation as it's called. We're going to explore solutions in 1D, 2D using this deflated continuation method. And we're going to see also some new solutions that we were able to obtain over the years, and also some challenges that one encounters while solving such type of higher dimensional problems. And then I will wrap up this talk by going through some new challenges, ongoing research, and future research directions. Okay. So wave phenomena, waves themselves are disturbances that can transfer energy through medium. Waves without energy cannot do anything, and without energy, waves cannot do anything as well. They cannot transfer those disturbances. They are a defining feature of our universe. They can help us explain a lot of phenomena in physics and engineering, from the propagation of electromagnetic waves, acoustic waves, X-rays, and so on. So what happens is that if you're sitting on a pond on a rainy day, which is quite rare in California, although last days in San Luis Obispo we got some rain, you can see falling raindrops that carry energy, and through the friction and pressure, you can transfer this energy to the surface of the pond, creating all those ripples, those disturbances that propagate over time. We have been quite fortunate enough to live in the Central Coast, where we are quite familiar with ocean waves. Wind blows across the surface of the ocean, creating those waves in the ocean. Sometimes could be quite dangerous, especially if you think about tsunamis, about rogue waves, as they call, which is another research direction of mine. Also, at the macroscopic level, any violent disturbance of the fabric of space-time, if you think about a binary system of neutron stars, in particular, those disturbances, this violent acceleration can cause disturbances on the fabric of space-time that can generate the so-called gravitational waves, first predicted by Einstein himself. They were found, I think, in 2015, if I'm not mistaken, by the LIGO experiments. That was also the Nobel Prize in Physics. Now, at the microscopic level, we have light waves, where white beam, it's an optical, it gets diffracted, you get different frequencies, different wavelengths, different colors if you like. But also the structure that I'm interested in is that the microscopic world, matter itself can behave as a wave. So you do have the so-called particle wave duality, as it was first realized by Louis de Broglie, also Einstein himself proposed the photoelectric effect. The matter in some cases can behave as a particle, light can behave as a particle or as a wave, so you have the particle wave duality there. Now, talking about matter waves, as we said, there is something really cool about that is if you take a collection of such subatomic particles and you pull them down to absolute zero, theoretically speaking, something really nice can happen is that each particle has a specific velocity, and as you cool down the temperature, the velocity goes to zero. And since the wavelength is inversely proportional to the velocity, or the velocity is inversely proportional to the wavelength, what you have is that you have large wavelengths such that now all those particles start communicating with each other. So what happens is that you can describe macroscopically this state of many particles at such extremely low temperatures by just one descriptor. That descriptor is a wave function, a single wave function. So this is the Bose-Einstein condensation. It is a state of matter in which a number of particles are the same quantum state, first realized theoretically by Bose and Einstein, but in order to have such available experimental technology, 70 years had to pass until two groups. One is the Joint Institute of Laboratory Astrophysics in Colorado, and the other one at MIT, led by Boffman. Generally, they considered rubidium and sodium atoms, and they started cooling this collection of particles close to nanokelvin. And something magic happens is that you have this overpopulation of those particles in regions in space. And for us in applied mathematics, we like to think of them as localized pulses, as localized solutions that we call them solid. Okay. Now, when it comes to modeling those structures, the equations that you get are nonlinear, so you have to do numerical simulations. Although you can get some insight from spatial limits, as we will see in this talk. Just a quick overview about Newton's method. So when it comes to the solution of such nonlinear PDEs, you discretize them in space, pick your favorite method, finite elements, finite volumes, finite differences, spectral methods. At the very end, you're going to get a large system of nonlinear equations that you have to solve. So in Newton's method, what you do is that you have a root finding problem. Now, I mean, I have that's a scalar one. You just generate a sequence of iterates. Then for convergence, and then goes to infinity, you just get the original problem. Essentially, the method of tangents. If you like it, instead you construct the tangent and you find the x-intercept, and then you keep iterating over and over. The nice thing, which is I think that the key message here, is that you can generalize it to systems of nonlinear equations. Now you have your nonlinear residual, it's Jacobian inverse, or the percent derivative inverse, if you like, and numerical analysis would not invert matrices because they're really expensive. Instead, you just solve a system of linear equations, which I think is one of the most fundamental problems in scientific computing. You have eigenvalue problems, systems of linear equations. Again, if you want to solve a nonlinear system of equations, you just solve a system of linear equations, which is quite nice. So you can now bring forth all available methods that you can think of, from numerical linear algebra, direct methods, iterative methods, power solvers, and so on and so forth. Now, when it comes now to the solution of such large systems of nonlinear equations, there is one question. The question is, are there more solutions to my problem? Can I find them? Well, that idea goes back to the 60s, where Wilkinson said the following: if you have a root finding problem P of x equal to 0, and you have found, let's say, k roots of that polynomial, you may be able to find more solutions by not solving P of x equals to 0, but solving Q of x equals to 0, which has now this form P of x over the factorization of those solutions. Okay? Later on, 2 years actually later, Kenneth Brown and Gerhardt, they said, well, if I have now a system of nonlinear equations, f of x equals to 0, I may be able to find a new solution by not solving f of x equals to 0, but just solving the deflated problem, the g of x equals to 0, which consists of your original nonlinear residual times this operator, this deflation matrix, as I call it there, which I like to think of this as a repulsive potential in the following sense. In the course of Newton iterations, if your iterate is close to x star, it will push Newton's method away from that solution that you have found previously. Okay? However, there is a danger. If you really move far away from that x star, that distance might be quite large, so 1 over something large might be 0 or close to 0, and then Newton's method might erroneously convert to something that is not a solution. Okay, so that problem was bypassed in 2015 when people started realizing this method in the framework of PDEs, when you have now systems of nonlinear equations, by including this shifting, this sigma here, which accounts for that. Okay, so now we have a modified deflation operator, I would say. This P essentially specifies this strength of this repulsing force, I call it, and it has a nice property that this deflation operator preserves the solutions of your original problem, and if Newton's method converts to a solution, it will convert to a new solution. That's really nice. So I also wanted to show you like a very simple implementation of MATLAB, just like in one-dimensional problem. I'm going to pick now a cubic polynomial, okay? And I'm going to I'm going to type down the coefficients, let's say minus 2.1, 0.1, 3, for example. So I'm just using Newton's method. I have also to, what is my graph? Oops, I have to, let me close this for the time being. Okay, I had one window open there, so there it is. Okay, so let me copy paste the same coefficients. Fine. Okay, so here is a graph of my polynomial. Newton's method found one solution. Now I'm going to deflate this solution using that operator. I'm going to find the second solution. I'm going to deflate now row 2, which means I'm going to multiply my residual with that deflation operator for that root. I'm going to find the third solution. Now I'm going to deflate those 3, but there are no other solutions, so Newton's method will reach the maximum number of iterations that you have described in the code, and then it will stop. Okay. Now let me also show you this for a system of two equations. So let me do this. So you have a system of 2 equations. You are looking for points of intersection on the xy plane or x1, x2 plane, as I have it here. When you start with an initial guess, fire off Newton's method to find one solution, you deflate this solution, it's gonna convert to one more solution there. You deflate now those 2, you find the third, you deflate those 3, you find the fourth solution, you deflate those 4, and there is nothing else in Newton's method that will convert to anything else. It seems there are no other solutions. Okay, just to give you the idea. Okay, so now this is interesting because there are many other problems that we are very much interested in that involve a parameter. So when you cast, let's say, a nonlinear problem, you might actually have a parameter. I'm calling it lambda. That could be, for example, if you're looking, let's say, for traveling waves, it could be the speed of a traveling wave. If you're looking, let's say, for breather solutions, in lattices, it would be the frequency, but it is a parameter that you want to trace solutions as this parameter there. Okay, so you're looking for solutions as lambda is variable. A continuation method is essentially an algorithmic procedure that can actually trace such branches as this parameter is variable. Commonly used methods, you have the natural or the sequential method, where for some parameter value lambda naught, you have used Newton's method, you found x naught, and then in order to find the solution at a different value of lambda, let's say lambda 1, which is far by delta lambda to lambda naught, you use this as an initial guess, so you use Newton's method, and you find the other solution in France. However, the sequential continuation as it's called fails when you have turning points, where you have essentially a vertical tangent. So that's a problem. What else can you do? I think back in the 80s, Eusebius Gödel, Kerneves, and Kuznetsov, they just considered the pseudo-arithmetic continuation method, where now you perform the continuation over the array. So it is essentially a predictor-corrector method. So you essentially move along the tangential direction by delta S, and then you use Newton's method as a correction in order to find the point in your bifurcation interval by this code. Now, if you combine the deflation technique and the continuation method, now you can construct a quite, I would say, interesting method, the deflation continuation method. But before doing this, let's actually see the following. Suppose that you have a one-dimensional problem, and you use pseudo-arithmetic continuation method, you find this branch. So I'm just using this polynomial of degree 4. And again, the question is, are there more solutions to my problem? If you are brave enough and you play with different values of lambda, different initial gates, you might be able to find another solution. Then you can use a continuation approach and find the other branch. But clearly, the pseudo-arithmetic continuation doesn't tell you anything about the existence of this branch. And the question is, what can we do in order to be able to trace this branch? Is there any possibility? The answer is maybe yes, because if you combine now, as I said, the deflation and continuation, you have the deflated continuation method, or the DCM as they call it, is that you fix your parameter lambda, you try to find as many solutions as possible for that fixed value of lambda, you deflate it step, all those solutions that you find, and then you can move either sequentially or by using pseudo-arithmetic continuation. So coming back to this problem now, I'm cheating because I know that there are two branches of solutions there. Suppose that you have that you start with an initial guess minus 0.1 and lambda equals minus 8, so you are somewhere here, and when you can convert it, you're very close to this solution. You're gonna find that solution as well. You deflate now those two. There is nothing about it. There are no other solutions to the problem. Newton's search is terminated. Now you start moving sequentially towards positive values of lambda. At some point you're going to arrive here, and there's a method that at each point you deflate all those solutions. You can keep moving now towards the right. At some point, when you deflate those two solutions, you're going to find the other one, which is on the upper branch of solution. So this way you can trace the entire disconnected branch. Okay. Now this becomes quite handy when you do bifurcation analysis in nonlinear PD. That is the message here. So let's now focus on matter waves. By the way, I couldn't resist to include the type of pink floyd, the side of the moon, for highlighting the diffraction, but just for the sake of time, I think we should move on with this. Quantum mechanics, matter waves, we have a matter wave, which is essentially, its mathematical description is based on the wave function. And if I remember correctly from my undergrad quantum mechanics, I think it was Max Borg who was who actually said that the physical meaning of the wave function is not the wave function itself, it's mod squared, which connects with probabilities, essentially the probability of finding a particle at position r in the time t, and if you add all those probabilities, you get one, which is certainty. Essentially, you can take this integral. So the wave function is a solution to Schrödinger's equation, written here. The H node is a Hamiltonian. It involves the kinetic energy term and the potential energy term. When we want to find a solution to this problem, you do get essentially an eigenvalue problem. You do the separation of variables. Here is the energy level of the system. Phi is going to be the eigenfunction. It is a simple problem, and one problem that we have seen, I mean, when we were taking a quantum mechanics class, was the quantum harmonic oscillator. You have a parabolic potential, an external potential of this form, and the reason that I'm going through this is that it will provide us a lot of information when it comes to the nonlinear problem. We will see this in a bit. So the external potential is of this form. You can use a series to solve the problem. You will get a Fermi differential equation. You will construct the recurrence relation there for the coefficients of the power series, and you will see that the power series, well, the power series truncates. If you quantize the energy, essentially you get this expression where n essentially the quantum number describes the energy levels of the system. So the eigenfunctions in this problem are expressed in terms of the well-known Fermi polynomials modulated by a Gaussian. For n equals 0, you have the lowest energy state, the ground state of the system. I'm just graphing the modulus phi squared, the probability density, if you like. The n equals 1 is the perfect excited state. If you graph the solution itself, you will have 1, 0 crossing. For For n equals 2, you have 2 zero crossings. The second excited state, the third excited state has 3 zero crossings. You can also generalize this idea to the two-dimensional NLS. Now, your eigenfunctions will be products of determinate polynomials along the x and y directions. But you can also study the problem in polar coordinates where you will have a radial part that connects with Laguerre polynomials, and the azimuthal part describes essentially the z component of the angular momentum. So here I'm just showing you a few of the eigenfunctions. The ground state, the 0, 0. You have two quantum numbers. M and N essentially in Cartesian coordinates deal with a number of zeros along the x and y directions respectively. The first excited state is the 1, 0. The second excited state is the 2, 0 state, or the 1, 1. In that sense, it is a degenerate state in polar coordinates. You can have the ground state. The first excited state has an L equals to 1. So this solution is what we call as a vortex solution with charge 1. Then the second excited state can come up into two flavors: the vortex of charge 2 or a ring with a zero density, and that's what we call as the ring dark solid. Now, this now becomes quite interesting when you study Bose-Einstein condensates, because the model that you are solving is linear Schrödinger equation plus a nonlinearity. The nonlinearity is a cubic nonlinearity. It's coming from, it depends on the context that you are coming from, because this PDE, this is the nonlinear Schrödinger equation. It can come from nonlinear optics, or it can come from atomic physics. There are many derivations out there. In the paraxial approximation, if you're working with optics, or from atomic physics, there's a nice derivation in this book by Stengari about this PDE. Essentially, the cubic nonlinearity that comes up is due to the interatomic interactions. So those particles interact in the condensate. We're going to confine them, as this happens in experiments by optical lasers. The potential that is used is this again parabolic potential. Now, depending on the sign of the nonlinearity, you can have attractive interactions. If gamma equals to -1, if you're working with optics, that corresponds to a focusing nonlinearity. If gamma equals +1, it corresponds to the repulsive interactions, or the defocusing NLS as it's called. And the measurable quantities, and we're doing quantum mechanics, is the mod phi squared. Okay. Now, a special case for the NLS is when you do not have this potential term in 1D. The model is what we call as integrable, meaning that there exists an infinite number of conserved quantities. For gamma equals -1, for a focusing nonlinearity, an exact solution does exist there. It has the form of a hyperbolic secant, where its spatial profile is shown here, the mod square. It has a bright bump. It has a bright bump, if you like. That's why people call it as a bright soliton. It is a dynamically stable solution over the time propagation here. On the other end, when gamma equals +1, for the defocusing NLS in 1D with no potential, there is another solution, explicit solution, that can be found. Actually, both of them can be found either by using the integrable system techniques, the inverse scattering transport, if you're interested, or direct methods like the Rother's method, and so on. The other solution is gamma equals +1 is the hyperbolic tangent. Is in the form of a hyperbolic tangent. If you graph the spatial part of the solution, it has this form, and you can think of this as having atoms here, atoms there. There is a density deep in the middle, so there is a dark spot, if you like. That's why people are calling it the dark soliton. It's also a stable solution in the course of the time propagation. Since the model is integrable, you have infinitely many conserved quantities. The very first three are shown here. They're associated with symmetries of the NLS. The NLS is invariant under phase rotation, so that gives birth to the number of atoms. It is also invariant under spatial translations, giving birth to the conservation of momentum. It is also time translation invariant. It gives birth to the energy conservation. Those are coming from Nether's theory. But now, if you have a potential in your problem, especially in higher dimensions, the question is, how can you solve the problem? Well, you can try to separate space and time, as we did for the linear scenario. You do get now this non-linear problem still, but you can start thinking of special cases here. Well, the first case, the simplest case that you can think of is, well, if the non-linearity is so weak, such that I can neglect it, which corresponds to that those particles do not interact with the condensate, what I recover is the quantum harmonic oscillator that I know how to solve it. I can solve the problem by using those Hermite eigenfunctions in Cartesian coordinates or the Laguerre eigenfunctions and so on. So you know how to solve this at the linear limit. Now, if you keep pumping atoms in your condensate through this parameter mu, which connects with a number of atoms in the condensate starts becoming fatter and fatter and fatter, so there is no room inside the condensate in order those particles to move. So all those spatial variations go to zero, so you get an explicit solution that is called the Thomas Fermi solution. And the question is, what is happening between those two limits? So what is happening between these two limits is that you use continuation. In 1D, what you do is that you discretize your problem using finite differences or finite elements or spectral methods. You pick any of the linear eigenfunctions as initial guesses to your Newton code, and then you just do a continuation all the way to larger values of mu. So for the ground state, you see that it starts getting fatter for large values of mu. Same thing for the first, second, and third excited state. Those are essentially the Thomas Fermi solutions in that context. So I'm just monitoring the number of atoms of the more squares. But in 2D, there are some surprises because you can pick your ground state, you can do the continuation all the way to the Thomas Fermi. If you pick the first excited state, which can come in two flavors, either in the Cartesian decomposition or in polar decomposition, the vortex solution, you can do the continuation all the way to the Thomas Fermi. I will come back with the coloring shortly, but for the 1-0 state in Cartesian coordinates, something is happening here, giving birth to a new branch that has two vortices, and somewhere there, something else is happening, giving birth to three vortices. So now, as we increase the dimensionality, the configuration space of solution starts becoming richer and more interesting. Okay? So in order to analyze all those branches of solutions, you want to study also the stability of those solutions. So when it comes to experiments, experimentalists would want to know whether such solutions are robust and they can be found in an experiment. In order to do that, you linearize the NLS about a sensory solution that we found by using these standards. You keep orders of epsilon, you get an eigenvalue problem of this form. Omega are the eigenfrequencies, and if all those omegas lie on the real axis, then your solution is called marginally stable. If you have any non-zero imaginary part, then your solution is unstable and can come up in two flavors, either as pairs of unstable modes or as coordinates, due to the Hamiltonian nature of the system. So what we did back in 2018, we used the deflated continuation method as follows. Pick the ground state from the linear limit that you know how to construct it, continue all the way to the Thomas Fermi limit, and then deflate now this solution once. You will find the second solution. Deflate those two, you will find the third solution. You keep deflating from the Thomas Fermi limit and then do the continuation backwards, such that you can find as many solutions as possible. We found many known solutions. That was actually a benchmark of the method. Now, all those solutions that I'm showing here have been found previously, and now my coloring here has to do with the stability threat of those solutions. The solid blue corresponds to stable solutions, red and green to exponentially unstable and oscillatory unstable solutions. Just to give you a few info about why this emergence of new branches is happening. It's happening because in dynamical systems, there is the so-called pitchfork bifurcation. You have a real eigenfrequency, a pair actually, that crosses the origin and gives birth to an unstable mode. So what happens at this bifurcation point is that the parent branch, which was this state, it was stable, it became unstable, and its stability nature was inherited by this vortex line. Later on, another zero crossing is happening somewhere here. Now, a second unstable mode is generated, although this solution is anyways unstable, that gives birth to this mode. So those are Pittsburgh bifurcations that are happening there. Okay. Now, just a demonstration about a few. Yes.
Is there any reason why the left pitchfork becomes oscillatory unstable for a small range of number states?
Oh, you mean the green? No, there is no.
They just have.
No, but that one, by the way, since it becomes oscillatory unstable, that actually gives birth to periodic orbit. So you can find now a periodic solution there. But here we're just interested in stationary solutions, not periodic orbit. So essentially you have a whole permutation there. If you want to actually find the periodic orbit. Yeah. It was quite rich. I mean, you got all those bifurcations there. But like for the stationary state, you have those pitchforks. And just a video about the simulation. If you start, let's say, from an unstable state where the dynamical system is driven to a nearby stable state, which is the vortex dipole in this bifurcation diagram. Okay. So in total, we found 63 solutions. Many of them were known, but 50 new ones. So here I'm going to comment in passing a few solutions that are known, like the solution that has two stripes. It gives birth to those three bifurcations, having three vortices on the left, three on the right. Vortex quadruple here. Here you have four vortices on the left and on the right. This is the soliton necklace, as people call it in condensed matter, giving birth to those two bifurcating states. But here is a subset of some solutions that have never been identified before. We were able to trace them using this technique, this deflected continuation method, especially with this bifurcation that has one side and three vortices on the left and on the right. We started getting really excited about this, and we said, well, let's now try to solve the two-component problem. The two-component problem essentially models a gas that consists of two different species of atoms. So you want to study how those interact. Or you can think of same species, but different spin states. So you have two wave functions, one phi minus and phi plus. And the mechanism for forming bound state in this problem is that the one component forms an effective or creates an effective potential in the second component, such that bound modes are supported in the second component. So you're looking for stationary solutions. Again, by the same answers, now you have two chemical potentials, two values, two mu's, one mu plus and mu minus. Plugging this here, you do get now a boundary value problem consisting of two nonlinear coupled BDs. We use experimental values of those interaction coefficients, which, by the way, the GIJ tells you how space 1 interacts with, how space I interacts with space J. It is like an attractive interaction or repulsive interaction, so we consider repulsive interaction here. So by fixing the mu minus, which sets the potential in the second component, the only continuation parameter or the bifurcation parameter was the mu plus. So a few results here. Here is an example of what we call the dark bright soliton. Here you have the soliton stripe that traps a bright soliton in the other component. There are again those pitchfork bifurcations. If you monitor the real part of the eigenfrequency omega, there is one such a zero crossing that such that this solution becomes unstable, giving birth now to this vortex dipole. Well, that's something that we saw from the one component. Remember that the stripe soliton gave birth to vortex dipole, that was a pattern. So you see now this pattern also in the two component problem. So this state from its inception, although it's not so clear in this panel, it is stable, but then it becomes unstable, and then it destabilizes itself. There is one such bifurcation later on that gives birth now to the vortex dipole. That's something that we have seen for the one component case. Now, a diagnostic that is quite useful when it comes to those businesses is that you can measure the total number of atoms difference with respect to the parent branch. So the parent branch is this one. So you measure essentially the difference between the difference of atoms from this state with respect to that one. So you can very carefully, like see where those solutions can be formed in the parameters. Now, another example of a radial state. Here is an example of what we call as a vortex bright ring soliton. You have a ring now of zero density there. Again, there is such a mechanism that gives birth to one peaceful bifurcation, that is the bifurcation state that comes from that point. And that one itself is unstable anyways, and there is one such an instability, one extra instability that leads to a secondary bifurcation that is shown here. So we're able to capture even secondary bifurcation by using those methods. Also, the second bifurcation of the parent branch of this ring state is shown here. It involves 1, 2, 3, 4, 5, 6 vortices, which is anyway n and all those results can summarize this bifurcation diagram. Now, something that I would like to mention in passing when I got involved in this problem was the following. Maybe you have better ideas when it comes to the computation of eigenvalue problems. When you study the stability of such type of systems, you have sparse matrices. You want to find the eigenvalues of a relatively large sparse matrix. In my case, it was roughly 360,000 by 360,000. I used AIDS, the built-in eigenvalue solver in MATLAB. And just to be clear, I haven't used any kind of shifting. Some people use the shifting very unknowingly. To me, maybe you know more about this, but the question is, what is the right shifting to use when it comes to those eigenvalue problems? I mean, do you know what is the correct shift? So I didn't use any shift. So when I tried to do that, I got a spectrum of those solutions that it was like that. It was kind of nice. Okay, MATLAB, I mean, didn't say anything about accuracy or any problems or nothing until I just checked something that is essentially a relative error of the eigenvalue that you have computed, and what I got was okay. So now those results are completely wrong.
Are you computing all the eigenvalues?
You are computing not all, but you're computing, let's say, 100 eigenvalues, 200 eigenvalues, not all of them. You don't need them all, because if you have any instability, those will come actually from those unstable eigenvalues will be really close to the origin, so you don't have to compute the entire. But the thing is that I was quite desperate because I spent like almost a year trying to figure out what is going on here. So this project was kind of doomed. Yeah, it was quite disappointing.
Okay. And I was just thinking
so here you have the stability metrics. I computed the right eigenvectors. I plugged them here. So essentially, that's something that I'm saying to my students, and sometimes I forget about it. You solve a problem, just plug the solution back to the problem that you're solving and see if you get satisfied. So I forgot about it. So I had to do this to my own, and then I thought, wow, this is wrong. This doesn't make any sense. So I started looking online to find a potential solution, and they came up with this commercial package called Advanced Fix that was developed by Pavel. Now I think I'm going to butcher his last name. He's a really called Boroko. I think he's in Japan. He developed this toolbox utilizing extended precision. You can carry out all those calculations, and the reason for doing this was the following. I checked the condition number of this matrix. It was something like 10 to the power of 19 or 10 to the power of 10, which means that it is really sensitive to finite precision. So I said, if I carry out the computation in extended precision, maybe I will try to keep those perturbations that are coming from finite precision to, just being as small as possible. Indeed, I did it using this package. I found a fantastic accuracy, but the problem was that I had one branch had 121 solutions over mu plus. That computation took 3 months, and I had in total maybe 40 branches. So I had to wait for years just to do all this computation. But when I was at UMass Amherst, I was quite fortunate to know Eric Polizzi. He is in the electrical engineering department at UMass Amherst. I knew that he has developed an eigenvalue solver, which is based on contour integrals I think it's still part of Intel's MKL if you have ever used it. And I haven't used it back then, and then I said, let me give it a shot. I used it, and actually we met together. I said, Eric, I have this problem, and I'm trying to do this, and he quickly tested, and everything worked nicely. I remember that I hugged him. I said, thank you so much. After a year of pain and struggle, now I can do this. And indeed, 3 months versus 40 minutes. So here is the combination. Here is the comparison between this eigenvalue solver, and this extended precision one in mapping. 40 minutes versus 3 months. I think it's definitely better. So that was quite an advancement, at least to me. Now we in the last 10 minutes, a few results about the 3D component. About the 3D-dimensional problem. Now one component. Using again this method, the deflated continuation method, we were able to find exotic new solutions here. This is the planar dark solitaire with a vortex line increasing the condensate. 2 vortex lines, those are generalizations of the vortex that I show you now in 3D. A vortex line star, 4 vortex lines, 2 vortex lines, and the vortex ring here, 2 vortex lines that they are interconnected with each other. Some dynamics using the Crank-Nicholson method, which is nice in terms of preserving the energy of the model. So what is happening in the dynamics is that those solutions are weakly unstable, quite good candidates for, I would say, for observing them in experiments. So now the instability is going to manifest itself. You will see that this structure is going to split into 2 vortex lines. They're going to reconnect. They're going to split. They're going to reconnect. So this keeps happening on and on. But again, the growth rates are quite small, which this is quite promising when it comes to experimentally observing those states. Okay. More complicated solutions that we were able to find. Another vortex line star structure. Here you have 1, 2, 3, 4 vortex lines. 1 vortex line perpendicular to this structure. Here you have vortex rings that connect the bottom and the top. A S-shaped vortex line with a vortex ring here. And those, something that Panos, my very good friend and collaborator, called them labyrinthine patterns of vortex lines. And some results on the dynamics. I'm going to show you just one. This is, I think, this 4 vortex line with 2 vortex rings connected them, and then the 1 vortex line that faces the condensate. So weakly unstable, but as time passes by, those split, they connect, which is quite cool. So the model itself prefers to form those vortices, those vortex lines, which of course it connects really well with superfluidity. So okay, now one last result about this problem was that we were able to find a bifurcation that comes from this planar dark solitaire with the vortex line. These solutions have never been reported before. It is unstable, but it was quite cool to find more solutions to this problem. Quite recently now, we considered a 3-component now NLS system in 3D. Now the problems are becoming really challenging. I haven't used deflation yet, but we were able to find using pseudo arc length another branch of solutions here. So this has to do with spin or condensate. You have atoms that they are oriented in a specific position, their spin, by using magnetic fields. And we have an experimentalist, David Hall, who carries out such experiments. And we're able to find a branch of solutions of what we call as half quantum vortices. Those are called Alice rings. So those are the 2 branches that we were able to find using pseudo arc length. But still, there are many interesting tools and challenges that one has to bypass when we work with such high-dimensional systems. So what I tried to tell you today was that we have many tools out there that can do a really good job in terms of exploring the configuration space of complex nonlinear dynamical systems. In some cases, those tools may fail when it comes to detection of disconnected branches of solutions. So the deflated continuation method that I show you could become a good candidate for discovering new solutions, at least what we have seen so far. and also studying their bifurcations and stability of those solutions. So, thanks to the French government, I am quite fortunate to visit the University of Rouen this summer. I got a scholarship, a fellowship from the CNRS. We'll be working with the numerical analysis group at the University of Rouen. They have developed this toolbox in finite elements of 3 plus. We are proposing to develop such a toolbox for studying such higher dimensional NLS systems. We are working towards implementing the deflated continuation method in that framework. Quite recently, one of the developers, his name is Pierre Jolivet, was able to integrate PETC and SLEXI with 3 plus. So now you can use all sorts of all those iterative solvers for systems of linear equations. You have now lots of options out there. However, I should mention that although it was ported with SLEXI, we have seen in some cases that SLEXI failed in computing sometimes the spectrum of such type of problems. Although it says that it converges, in some cases the results are not correct. We have seen it. So what I try to tell them then, let's actually try to integrate this, that eigenvalue solver, which is really great. I mean, you don't need any kind of a shift. Just say here is the contour, find all the eigenvalues in this inside of this contour. That's it. No shifting, nothing. Also, all this research effort has been spearheaded. From experiments by David Hall at Amherst College, and he has done so many great things, including 5-component condensates. Here is an actual experiment that he did a few years ago, and when it comes to a 5-component velocity density equation in 3D, if you want to do stability analysis, then things are becoming quite challenging. So you have to develop some, I would say, suitable techniques for tackling such type of problems. So I would like to thank my collaborators. So over the years, Panos Kibritidis is a good friend and collaborator. Over the years, David Cole, who is our experimentalist, he has his own facilities at Amherst College, conducting all those experiments at such extremely low temperatures. Patrick Fowler and Nicolas Bouleur, with whom we started this journey since 2016 or 17 or so. Ricardo Carretero Gonzalez, who is at San Diego State University, together with Mitun and Bianco, we found those Alice rings, this solution to the 3-component problem. Also, my collaborators at Los Alamos Laboratory, where we work on similar problems, Ahmad Saxena and Fred Cooper. Jimmy Adriazola, your own Jimmy, with whom we have some really cool problems that combine PCs and optimal control. I hope that we will do some progress during the summer, hopefully. Yeah. And then the French group, Younou Danal and Georges Sadak at the University of Rouen. Pierre Jolivet, who was the guy who actually ported PETC and SLEXI with 3FEM. Frederick Hess, who is actually the main developer, one of the main developers of 3FEM back in the 80s. And Boris Malamet, who is the leading figure in optics and PCs, who we have been having so many great exchanges scientifically and many other things. Also, the funding sources for the CAN support. This is a grant that I received last year, a standard grant from the NSF on studying collapse phenomena. It's a different direction, but many of the techniques and tools that I told you are directly applicable there. So with that said, a few references for your convenience, some works on the BECs and some works that I worked on with the group at Los Alamos. So with that said, thank you very much. And I would try at least to answer any questions that you may have. Thank you.
Yeah, I want to understand, on your computer, like this condition number issued for 10 to the 19th in pages, right? Pardon? 10 to the 19. 10 to the 19. You mentioned that was the condition number of the system, right?
Of the matrix.
Yeah, matrix. But the matrix is basically the Laplacian plus a potential.
The Laplacian plus a potential, yes.
So I'm surprised by that condition number because your potential
I was surprised as well. I was surprised as well. Well, maybe I think, in the two component case, you have essentially, this matrix has four blocks.
Yeah.
So, did I pass it? I think I passed it. Because I wrote just this is essentially the probability matrix if you have in one component. Okay, so you have the Laplacian, the potential.
Yeah.
Now, in the two component case, you have now four blocks. And, yes, I mean,
I got a question till that, it's diagonal still?
it is diagonal, well, it is sparse anyways. I mean, if you, let's say, find a difference, let's say second order calculus, what are you going to do? You're going to get kind of diagonal.
Yeah, but you expect, in that case, you expect a solution number of the order of 1 over the x squared.
Fine, but it's also dependent on the state.
So that's what I was gonna ask, right? So when you linearize, because you linearize around something that looks.
Around phi naught.
Yeah.
Around phi naught.
Okay, so phi naught, but phi naught, I guess you can have a peak.
Yeah.
Even though it's normalized to 1 in 2 norms.
You do not normalize the solution to one. You do not. You do not. No, you do not.
But even if it could have a peak, I mean, it could be really large in some region, so that's something.
That might be the reason that contributes to this condition behaviorable. That matrix, yeah. But yes, I mean, if you remove the stuff, there's no reason then.
Or even if you use the potential, standard potential. Unless
Yeah.
you put something very large, this is something you should,
Yeah.
you do not expect like that.
Yeah. I agree. Yeah, I agree. I agree. I was also surprised. It was a struggle for many months.
And then can you go back when you showed the solution for you said Thomas Fermi?
Oh, yeah. Okay.
So, no, the next one.
Oh, the next
Yeah,
one.
the pictures are a bit confusing because for Thomas Fermi, you said you have, is the case when the slow variation in
Yeah.
density.
Slow variations in the
Gradient. So that
Yes.
that you expect slow.
you have slow variations. Yes.
Yeah, but if you look at the solution that you have in the core, there's 5 variations, right? So I guess the solution is Thomas Fermi outside of the core or something.
Oh, yes.
Sometimes you convert it, but it's a weak.
Yes, well, no, yeah, I see what you're saying. Well, I see. Well, I would say that the Thomas Fermi solution, just to be clear, is essentially this one.
Yeah.
This one, but I should have said that this is the first, second, and third excited states at the Thomas Fermi limit, but those are not the Thomas Fermi solution.
That's sort of.
Yeah. You're 100% right. Yeah, absolutely.
You don't actually use the Thomas Fermi solution at all.
You do not. No, but you can use it. I mean, if you just replace the V of R with the parabolic potential, you can actually use it as an initial guess. You can start from the Thomas Fermi limit, but just for this solution.
Have you tried that? Oh, yeah, okay, that's what I.
Yeah,
Because this one might take a long time to convert for the oscillation, right? Generally.
Yeah, well, but again, you cannot start from the Thomas Fermi limit from the get-go. If you have like those excited states, you can obtain those.
Yeah.
You start from the linear limit, from the other end, from the low density. And you can do the continuation towards.
Yeah, that's.
Yeah. But that's actually the point, yeah. Okay.
So with the five component.
Yeah.
That you showed, that just means 5 different species of particle.
5 different species.
What was FZ in the 3 component case?
I think I haven't written that.
Go back. Yeah, FZ.
I haven't written that. So that's if I remember correctly, the magnetization field in the Z direction. If I remember it correctly. Yeah, I should have actually included that. It is,
I guess,
you have bias fields there that you can actually polarize all those states along a specific direction.
I guess I'm surprised to see it there and not coupled with momentum in the
Mm,
Hamiltonian.
yeah,
Because I figured that it was probably the magnetic field, but
yeah,
I thought that it would appear in the.
yeah. I should have written more about this because I thought that maybe I'm gonna run out of time. So at least let me mention about
But is it constant in the model?
Yes, no.
It's not.
No.
It depends on. It depends on space.
I have to look at it.
But it's
Okay.
fixed, I mean, it's a given function.
Yeah.
And then, has anybody done any, so in that 2015 paper that proposed that did the deflation that
Yeah.
introduced the sigma and the p, did they discuss any, like, how those hyperparameters impact convergence?
That's actually, this is still a question for me, because people, I mean, I have seen that they say, and also we say that you pick this, you just square the out norm, and that's fine. You use sigma is equal to 1. At least those are the parameters they use in that silly simulation that show you MATLAB. That's what I use.
And then
It could, yeah, I mean, it could come, I use P equals 2.
you use p equals 2 and sigma equals 1?
Yeah.
Yeah.
But,
And if they work, so if it's
yeah.
not broken, don't. Try to fix it.
So we'll try. Let's try. I mean, it could affect the convergence. So let's actually do this. Let me see what I used here. Maybe I was playing more. So can I do this on the spot? Let me see. From audience, yes, because when I was writing this code, I said maybe I should ask just the audience to give me the parameters. So now I have.
Sigma equals 0.2 and p equals 2, right?
Well, oh, I have it there.
Yeah.
Oh, okay. So let's see. 1. Let's do 1 because I think I was playing with this. So let's do this one. So let's say, can you pick now some coefficients for this cubic polynomial? I don't know, like
How about
5,
1, 4?
1, 4, 1, 4,
3.
1, 4,
-3.
-3. Okay. Let's see what happens. Fine. Now we don't have a real metric because we also want to see the convergence, right? I mean, how this affects, because I think that was a question. I mean, it found those 3, so I think it's fine. But yes, I mean, it should affect the convergence.
Last time that
It went to,
left and right all over the place, but now for whatever reason that got bounded.
yeah, but did we use the same coefficients? I can't remember. Yeah.
All right.
Okay. Pardon?
1 was 2.1.
Oh yeah. Maybe I should have it somewhere here. What was that?
Yeah, that's right there.
Oh, there it is. There it is. There it is. Okay. So let me do this. Okay. Huh.
Oh, convergence is worse. Yeah.
It's worse, huh?
It took more
It took
iteration.
29, yeah. Mm-hmm. Interesting. Yeah, I mean, like you have those now knobs that you display around it. Speaking with Patrick himself, I mean, they said, well, we'll have tried this with another strokes and other kind of problems. It seems to be working well because it seems like one. But I think it's an open problem if you can adjust them to the problem that you're solving, if there's like some sort of an optimal set of those two parameters. Yeah.
And one last question.
Yeah.
When you plotted the solution to the 2-component system,
Yeah.
Were you applying the phase difference between the 2 components? Was that what was the bottom 2 panels? So
Yes.
the top 2
Yes.
panels were
Yes.
the
Yes.
absolute value, and then the bottom 2 panels were the phase difference.
This is actually the phase of the solution of the one of each of those 2 components. So, for example, here where you have the vortices, you can see that you go from -5 to 5 and like 1 vortex.
I guess the reason I asked is the phase of one of the components is never interesting. It seems like the left one's never interesting, and then the one on the right is a lot more interesting.
On the right, oh, you mean those?
Yeah, one's got constant phase, and then one's got
Yeah.
really interesting visual variation in phase.
Yeah.
Is there any good reason for that, or
Because if you think of how this trapping is happening, is that the one component creates this effective potential that can trap. So if you think about it, like let's say that in the one-dimensional case, if you have, let's say, the dark soliton, okay, and you trap, let's say, a bright soliton in the other component, right? You will have such a situation, right? So if you generalize this picture now in 2D, the one component is going to be the vortex. So you see some sort of phase information there, but for the other components, since it's going to be a bright structure, you see no phase interesting information, I would say. So if I have to give you a cheap answer,
In some case, sometimes when it's focusing in the when people.
In this case, The coefficient not necessarily, well, for the,
Putting things away.
yes, for the coupled NLS in the two component setting, you have to have no, it could be defocusing. It could be defocusing, yeah, because one component should actually support that solution.
All right, well, let's thank the speaker.
Thank you very much. Thank you. Thank you. So now I can stop sharing? Okay. Thank you. Thank you. Okay.
Well, that worked.